So we're going to talk about the semantics of reactor systems. And what I'm going to do is give you two very distinct approaches to building a mathematical model for these reactor systems. The first one is actually more broadly applicable and is based on a way of doing semantics that was originally developed for synchronous reactive languages. So I don't know if you've ever encountered these languages, but they're I guess among the best known ones are Estrel, Reactor, and SCADE is a commercial outgrowth of that. And SCADE is actually used to develop safety critical software at Airbus. And so these languages are really designed for use in safety critical systems. I'll close this at least part way because it's very noisy out there. Okay, so let's just start right in. And I'm using a different technology here because when you do math, it's very helpful to be able to write, and I can't do that on the screen there. So, okay, so first of all, we're going to start with a very simple formalism for reactors, which talks only about their behavior at a tag. So that's an instant. Okay, you can think of it. It's a timestamp microstep pair. Okay, and so the way that we're going to model the execution of a program, a network of reactors, is first, what is the behavior at a tag? And then how do you advance to a new tag? And then you just rinse and repeat, right? You determine what the behavior is at the new tag and so forth. So that's the way we build the model. So the first thing is we just index the tags in order to we don't really care what the time values are or what the microsteps are. So just assume that n represents the nth tag that is relevant. So the first one will be 0, 0. The second one will be whatever your program says. It might be, after one period of one of your timers, or if a logical action gets scheduled, it might be one microstep later, or whatever it is, okay? But n will index the tag. And then the idea is that if you have a reactor that has, say, one input port and one output port, then you can model the behavior at that tag by talking about what is the value on the input port and what is the value on the output port. But we have to augment the set of values beyond just the data type. And the reason is that we have to allow for the possibility of the absence of a value at a tag, which we represent with epsilon. But perhaps more interestingly, we also have to augment this with a representation for unknown. You don't know what the input is, okay? So this upside down T is used a lot in these kinds of formalisms. It's called bottom. And it'll be obvious in a minute why it's called bottom. Okay, but anyway, this symbol really represents the situation where you don't know what the input is. And then capital T in this case represents the set of all values that are allowed within the data type of the port. Okay, if you're doing Python programming, T is the set of all possible Python values, right? Because it's an untyped language. If you're doing C programming, then it depends on what data type you declare for the port. If you declare int, this will be the set of all 32-bit integers. Okay, is that clear enough? So we call T tilde the data type augmented with this unknown and absent. Right, so that's the first step, and the inputs and outputs will be represented as members of this set. Then the behavior of the reactor itself is modeled as a function, and the function changes with each tag, okay? Because the function will depend on local state variables. And so at each tag, you have a different function for the same reactor. But at each tag, you represent the behavior of the reactor as a function that maps this augmented data type into the augmented data type of the output. And for simplicity, I'm assuming that the data type of the input and the output here are the same, which, you know, they would be in Python because it's an untyped language. It's the set of all possible values. But in C, it might not be the same, but just, you know, we don't really care that much about the type system here. So we just have that simplicity. So you've got this function right here. It depends, the actual function depends on the tag, but at each tag you get a mapping. And the inclusion of unknown is important here. So typically, a reactor, if the input is unknown, the output will also be unknown, but not always. Right? Can you give me a circumstance in which at a tag, the input could be unknown and the output would be known? Yeah.
If you're at some limit of the sensor that you are,
Yeah, that could be one scenario. There's a simpler scenario though. Suppose you have a reactor that takes the input and reacts to it and produces an output driven by a timer, say. Okay, and suppose that this reactor is lexically earlier than that one. Right, so now at the time corresponding to the timer, then you don't need to know whether the input is present or not. You don't need to know what its value is in order to produce an output. Okay, so in this case, the function, even if the input is unknown, is able to produce a known output at the tag of that timer. And this is what enables you to have a feedback loop. Okay, the feedback loop, this is the thing that you have to internalize for this semantics. The value, when you create a feedback loop like this, at a tag, the value of the output is the same as the value of the input. It's not that, you know, the output gets produced and sometime later the input appears. No. The output and the input are the same value at the tag. Okay? So the function here is something that we're going to use where the unknown, the possibility of unknown is going to have to be gotten rid of somehow. All right? And that's how we're going to build the semantics. In fact, we're going to find that if unknown persists, you have a causality. Okay, and otherwise unknown disappears and all your values become known. They will be either absent or present with a value. Okay, so that's kind of a little preview of where this is going. Now, there's no problem modeling reactors that have multiple inputs and multiple outputs. You can augment this, all right? Very simply, if you have a reactor that has 2 input ports and 1 output port, then again, assuming all the data types are the same, then this at each tag you're going to have a function from you know, t squared to t tilde, right? Where unknowns are now possible as well. Okay, so a concrete example of this might be one where, you know, you've got an input that drives a reaction, an input that drives another reaction, and again, you know, maybe an output that, whoops, is driven by a timer. And now you can have a more elaborate feedback loop. Well, this would require an additional output, but you could have something like that, okay? In which case, there's 2 inputs and 2 outputs. And, you know, the interesting thing about this is that the function here presented with an unknown input here and an unknown input here, nevertheless has a known input here with value 1, say V1, some value V1, okay? But this is still unknown. All right? So what we're going to do is iterate this process And once you know that this output is V1, this is no longer unknown. This becomes V1, at which point this is no longer unknown. This becomes V2, at which point this is no longer unknown. This becomes V2. And now you have the defined behavior of the program at this tag. Okay? The interesting thing to notice about this is that this, the values here, V1 and V2, form a fixed point. So in particular, if I take this function f of n and I apply it to V1, V2, the result is what? It's V1, V2. Right? Whereas when the inputs were unknown, the result was not the same thing as the argument to the function. Okay? So this is called a fixed point. Right? And in general, with any function f, if f of s equals s, s is called a fixed point. That's just terminology that's used in algebra to talk about functions. And so the semantics of a reactor system is always going to be a fixed point at each tag. All right, so let's look in a little more detail how this works. So first of all, I want to first convince you that this model is actually completely general. It can handle any reactor network, including, for example, reactors that have no input ports. Okay, those are still functions, but we model them as functions like this, where the domain of the function is this same set t tilde, but raised to the 0th power. What does it mean to raise a set to the 0th power? It's not really the absence, right? So think of, familiar, let's talk about familiar sets. So the set of reals, right? You've done vector calculus, right? You often model three-dimensional space as members of the set R cubed and so forth, okay? So what could we possibly mean by R to the 0? I mean, R to the 1 is easy to understand. R squared is easy to understand. R to the 3 to the 3rd is easy to understand. What could we mean by R to the 0? Yes. It's kind of like a void input, right? But mathematically, any set raised to the 0th power just gets defined as a as a singleton set. Okay, why a singleton set? Well, think about just exponents in general. If I take any number n and I raise it to the 0th power, what do I get? 1. Right? That's just a property of exponentiation. So in set theory, people do something very analogous, and they simply define the 0th power of any set to be a singleton set. Now, a singleton set has a pretty unique property with regard to functions, right? If the domain of the function has exactly one element, it doesn't matter what that element is, right? The function can only yield one possible value, right? The domain has only one element. If you can evaluate the function, there's only one possible argument. It's a function. What makes a function a function? Well, a function is a function because if n equals m, then f of n equals f of n. Okay? Otherwise, it's not a function. Right? So if the domain has only one element, then n always equals m, and the function can only ever yield one value. And therefore, this is a pretty nice way to model a reactor that has no inputs, because it just means that the output value is entirely defined by whatever this function yields. Okay? So for example, concretely in lingua franca, I have a reactor with no inputs and I have something driven by a timer, that produces an output. Okay. In order to determine what that output is, I just need to know what the sequence of values are that are going to be produced. Say it's the counting reactor or something like that, right? So the function changes on each tag, but it can, at each tag, it can only produce exactly one value. Right? So even a function with no input, sorry, a reactor with no inputs can be modeled using this, function concept. Similarly, a reactor with no outputs can be modeled as a function whose codomain is a singleton set. Okay? That just means that no matter what inputs you give it, it always gives you the same output. So that's the same thing as saying there really is no output. Make sense? Yes. Right. Yes, this function will change over time. The output changes at each tag. Well, no, in this case, with this reactor, there is no output. So if you model it this way, there is an output, but it's always the same.
So even though the function is changing, that doesn't change.
That's right. Yeah. I'm glad you raised that point because that's a good subtlety. So just, to repeat that point, right? T tilde to the zero, in fact, any function to the zero always has exactly one possible value. So the codomain is the same for all n. Okay. So you can think of it this way, from the perspective of the semantics of lingua franca or any reactor system, the semantics doesn't really care what the reactions inside this reactor do at all. The job of the execution framework is simply to provide the inputs. And otherwise, whatever the function does is invisible. Okay. All right. So, okay, so we can model reactors with no inputs and reactors with no outputs. Now I'm going to show you that you can take any network of reactors and model it as a fixed point problem. Okay. And I'm not going to give you a formal proof of that. I'm just going to do a proof by example. You've got a network of 3 reactors like this. You can always take, in fact, any number of reactors, right? You just take the reactors and stack them and draw a box around them to create hierarchy. You've got a new reactor now with 3 inputs and 3 outputs, or equivalently, a reactor whose inputs and outputs are members of the set T tilde cubed. Okay, so this means that at each n, for all n, the job of the execution framework is to find S of n such that the function f of n applied to S of n equals S of n. Right? It's a fixed point problem. Everything is a fixed point problem. In fact, once you sort of get used to the math behind this, you'll start to see literally everything is a fixed point problem. It's kind of scary. Okay, so the interesting questions then become, well, does a fixed point exist? And is the fixed point unique? Why are those interesting questions?
Well, if the fixed point wasn't unique, then that would mean that there's some sort of non-determinism, right?
Yeah, if the fixed point isn't unique, then you could have a situation where the program actually defines more than one possible behavior. It means you've got a non-deterministic program. Okay, that might be okay, But, you know, we've had this emphasis on determinism, and so we'd rather have a deterministic program where the behavior is in fact unique. And I'll show you exactly what the conditions are that guarantee that. Okay. And of course, if no fixed point exists, that means that you can't find a behavior, so the program doesn't have a behavior, which ideally you would like that to turn into a compile error, okay, rather than a program that can be executed but exhibit no behavior. That would be pretty strange. Okay, so these are fairly key questions, right? So just to convince you that even a problem that doesn't look at all like a fixed point problem, right? A reactor with an output feeding a reactor within it, but is still a fixed point problem. All you have to do is very mechanically just stack up the reactors, draw a box around them, aggregate the inputs and outputs, reduce everything to a fixed point problem. Okay. All right. Now, in order to understand whether the fixed point exists and whether it's unique, we're going to need to develop a mathematical framework to deal with these functions. And the framework that we're going to use is partially ordered sets, right? And the partially ordered sets that we're going to use are particularly simple in this case, where if you have, suppose your data type is 32-bit integers, okay? Then capital T is a set 0, 1, 2, up to 2 to the 31 minus 1, and then minus 1, minus 2, and so forth. Right, it's that set of numbers. So it's just a big set of numbers. All right, and we augment that set with bottom and epsilon representing unknown and absent. And then we define an order relation, which is called a flat topology, in fact, where bottom is at the bottom. In fact, that's why it's called bottom. And everything else, whoops, everything else is above it. Epsilon, 0, 1, 2, up to 2 to the 31 minus 1, minus 1, minus 2, etc. These are all above bottom. Okay, so this kind of diagram is called a Hasse diagram. And it shows an order relation between these, not between these elements of this set. Okay, now, major point of confusion. Suppose I write this order relation using, let's use a little squiggly less than. All right. Is it true that 0 is less than 1? It's not. Right? You've got to realize we've just defined an order relation that's not the normal numerical order. This is not true. It's also
and they're not even comparable in this, right?
I'm sorry, was there a question?
In this, 0 and 1 is not even comparable, right?
They're not comparable, exactly. So it is neither true that 0 is less than 1, nor that 1 is less than 0 in this order relation. Okay, so any two elements of the data type are incomparable. They have no order relation between them, which is the presence of incomparable members of the set is what makes this a partial order. Okay, posets is what partial orders are known to their friends as. Okay, partial order just means that there are elements of the set that aren't ordered. And in fact, in this flat partial order, most of the elements of the set are unordered. And notice, in fact, that absent is treated just like all of the possible values of the data set. It's also incomparable with the numerical values. And all of these have the property that bottom is less than epsilon, bottom is less than 0, bottom is less than 1, etc. Okay? So this is called a flat partial order. Now, I should point out, I wonder if I can get a new blank page here. I'll just use this page. So this partial order can be augmented to deal with tuples. Okay, and I'll show you how to do it here. Okay, I'll draw a Hasse diagram for, let's consider t tilde squared. Okay, so that's pairs of numbers. Then the bottom element becomes a pair of bottoms. And then just above that are elements where one of the two elements is known, one of the two elements of the tuple is known, but not both. So for example, absent and bottom, or bottom and absent. Okay. 0 and bottom, or bottom and 0. Right? These are one layer up. Then above that is absent and absent, absent and 0, absent and 1, and so forth. Okay, and notice then that absent and absent is also above bottom absent. Okay, and then this has 0 and absent, 1 and absent, etc. All right. So what happens when you have multiple inputs and outputs is simply that your flat partial order acquires a new layer, and it becomes deeper. All right. And the depth will always be equal to the n, the size of the tuple. Right. So in a program, again, going back to our generalization, okay, any program, any network of reactors can be reduced to a fixed point problem, where at each tag you have a function that maps t tilde to the n into t tilde to the n, where n is the total number of connections between input and output ports. Right? Because every connection gets pulled out. That makes sense? Okay, so we have this partial order relation, and now whenever you have an order relation, you can talk about functions that are monotonic in that order relation. So in particular, a function is monotonic with respect to some order if you take two ordered elements of the set and you apply those independently to the function, then the result of the function is also ordered. Okay? So this is pretty much the same as the usual intuitive notion of a monotonic function, which would be one that is always increasing. But, right, if you have, here's a function from reals to reals. Okay, you have the real numbers, you have a function of the x-axis. If the function is always rising like this, then if you have a t less than p, then you are assured that f of t is less than f of p if the function is monotonic, right? That's the usual notion. So the only thing we're doing here is generalizing that usual notion to partial orders and saying, as long as you have an ordered pair, if you apply the function to the ordered pair, you get an order relation that preserves the ordering of the arguments. Okay? So now we're going to find that the criterion for a program to be deterministic is that at each tag, every reactor has to implement a monotonic function. in this order relation. Okay, why is that? Well, turns out it's because of a rather powerful theorem called the Clainy fixed point theorem, which says that if you have any monotonic function on a partially ordered set, this is a particular variant of the theorem that deals with sets with finite depth. Okay, there's much more interesting versions that deal with infinite depths. Sounds like there's squirrels in this area. So if you have a monotonic function on a partially ordered set with finite depth, then you can construct a set that that is just the function applied repeatedly to bottom, whatever the bottom of your partial order is. All right. That set will turn out to itself be an ordered set, a totally ordered set, because of the monotonicity of the function. And so we call that a chain. And then the least upper bound of that chain will be the least fixed point of the function f. And it'll always exist and it'll always be unique. All right? That makes sense? So let's see how this would play out in a particular scenario. So let's take an example like this reactor that has a timer, and at each tick of the timer, say it produces the number 42. Right? Why is that a favorite number among computer scientists? Well, it's because of Douglas Adams' Hitchhiker's Guide to the Galaxy. Right? This is the answer to the ultimate question. We've lost track of what the question is. All right, so this reactor at each tick produces the number 42. We feed back to the input. Okay, so the question now is, well, all right, f of n at each tick n, let's say n now corresponds only to the times that the timer ticks. Okay, if there's nothing else going on in the program, then that'll be the case. Right? These are the only events that occur, so these are the only tags at which we're going to be evaluating values of the program. All right, so at each f of n, at each n, f of n is a function that, given any input at all, okay, call it x, yields 42. Right? So the question is that a monotonic function? Okay, remember now our T tilde is the set of bottom, absent, and all the integers, right? 0, 1, etc. Okay. And so, and the order relation is that bottom is underneath everything else, including 42. All right. So if I evaluate this function on bottom, I get 42, right? Bottom is less than 42 in this order relation. And this should be actually a less than or equal, sorry. That's the way this is expressed in this theorem, right? Whoops. Hey, go away. So bottom is less than or equal to 42. So that implies that f of n of bottom should be less than or equal to, f of n of bottom should be less than or equal to f of n of 42. Is it? What is f of n of 42?
Yes, because of reflexive, because it's a reflexive relation, right? So
right. Yeah, so f of n of 42 will be 42. right? If the input is 42, the output's still going to be 42. If the input is bottom, the output is 42. So this function is monotonic. And as a consequence, the Clainy fixed point theorem applies. We can form this chain. I'm not totally sure how to add pages to this, so let me just erase this. So the chain C consists of what? Well, n is the natural numbers, so f of 0, f to the 0 of bottom is just going to be bottom, right? F to the 1 of bottom is 42. F squared of bottom is just f applied to f of bottom, right? If f of bottom is 42 and f of 42 is 42, then all subsequent elements of this chain are 42, but this is a set. So the 42 actually only appears once, right? You can't have this in a set, elements don't repeat. So the chain C has exactly 2 elements in it, bottom and 42. It is an ordered set, and the Clainy fixed point theorem says that the least upper bound of that set is a fixed point of this function. It also says it's the least fixed point, right, which is 42, and we define that least fixed point to be the behavior of the program. Make sense? I really need to find a way to add pages. Let's add a page. No, does that add a page?
On the 3 dots, I think you can add a page. Below on the pages.
No, I don't know how to do it. All right. Let's take a slightly nastier example. Okay. Suppose that I have a lingua franca program that looks like this. Okay. I have a reactor that wants to produce the number 42, but it's triggered by the input, and I've put it into a feedback loop. Okay. So let's redo our analysis. For this particular reactor, what is f of n of bottom? The input is unknown. You don't know whether it's present or absent. Okay? And you have a reactor that has a reaction triggered by that input. And the reaction produces 42. What if the input is unknown, what should the output be? No? Because you can't invoke the reactor. Right? The reaction is triggered by the input. The input, you don't know whether the input is present. So the output remains unknown. Okay. So what is the chain C? Well, if I apply the function f to the 0 is always going to be unknown. F to the 1 of unknown is still unknown. Okay. So my chain C actually consists of only a single element, bottom, and that's already a fixed point. In fact, well, you can see it right here. It's a fixed point, obviously. So the behavior of this program is unknown. So what happens if you enter this program into epoch? Yeah, it's a causality loop, right? Shows up in red and says you can't do this. Yeah, I can't compile this program. And the math here tells you why. The behavior is unknown. Okay, that's the only possible behavior. It's the only fixed point of this function. Therefore, the correct answer is for this program is that the behavior is unknown, which is exactly what the compiler does for it. It tells you that the behavior is unknown. Okay. So the Clainy fixed point theorem, which is actually very easy to prove, but I'm not going to prove it for you because just take my word for it. Okay. But this gives us a very powerful result, and the only thing really that it requires is that this function be monotonic. So let me show you what kinds of behaviors would make the function non-monotonic. And then we'll see that those behaviors do not arise in lingua franca. Okay. So suppose that I have well, actually, I could use the same example where you actually can't write a lingua franca program that will be non-monotonic. Okay. But let me try to do it anyway. Right? So suppose I have two inputs that trigger reactions, and both of these reactions drive the same output. Okay. And suppose that this reaction writes 42 to the output and this reaction writes 43 to the output. Okay. Then it looks like there could be a possibility, right? Suppose that I've got some input here that is present, right? Some value at the input, I don't know, value 1, and this guy is unknown. Okay, then you should get 42 on the output, right? Because you can't invoke this reaction. You don't know whether to invoke the second reaction, right? The input is unknown. You don't know whether it's present, but you do know that the first one is present, all right? Now, suppose that I feed this into some other downstream reactor that has a reaction. Can this reaction ever see this 42? You guys maybe haven't gotten yet quite enough experience with lingua franca to know the answer to that, right? But it would be potentially very problematic if it could. Because, you know, it might change a state variable and then only later does it discover that, well, the value of that output actually should have been 43. So one of the things that lingua franca guarantees is that a reaction here will never be invoked until all upstream reactions have either been invoked or it has been determined that they should not be invoked. Which could occur, for example, if this input, instead of being unknown, was absent. Okay, so if this input is actually absent, this downstream reactor could see 42. If this input is not absent, but is any present value at all, okay, then this will not see 42, it'll always see 43. The lingua franca compiler guarantees that every upstream reaction either gets invoked or it has been determined that it is not going to be invoked at that tag. All right. So as a consequence, let's look at the possible behaviors, right? Suppose that the downstream reactor could see 42 when this was absent. Okay, that would mean that the function when applied to 1 comma bottom yields 42. And the function when applied to 1 comma 1 yields 43. Is that function monotonic? Actually not, because 42 and 43 are incomparable. Okay? It's true that 1 comma bottom is less than or equal to 1 comma 1. So that should imply that f of 1 comma bottom is less than or equal to f of 1 comma 1. But in this case, that's not true, because 42 and 43, 42 is in fact not less than or equal to 43 in this ordering relation. Okay? So if that 42 could be visible to the downstream reactor when this is bottom, then the function implemented here would be non-monotonic, and we couldn't use the Clainy fixed point theorem to determine the behavior of the program. So lingua franca guarantees that these functions are always monotonic by ensuring that the order in which reactions are invoked is always determined by the precedence order that is expressed in the program. Okay. So this theorem is very powerful. So let me go through a concrete example of a lingua franca program that has the same structure as this general picture, right? So we got a program that has 3 reactors. And it's a very simple program. The first reactor here is triggered by a startup. The second reactor has 2 reactions. The third reactor has just 1. Okay. We do the same trick to reformulate this as a fixed point problem. We just stack the reactors and encapsulate them in a container reactor and expose all the signals between them. Okay, so there's a total of 3 connections between ports. So now those are all exposed. And we have one big Mongo function f that takes 3 inputs and produces 3 outputs. All right. And there's actually one thing that I forgot to point out. The least fixed point of this function is something that you can actually constructively determine because the depth of the partial order is finite in our case. Always has finite depth. The depth is equal to the total number of signals. All right, as a consequence, the set C always has a finite number of elements in it. And all you have to do is enumerate them in principle and find the greatest one of them, and you've got the behavior of the program. Okay, so this is not only an existence proof that there is a fixed point and it's unique, it's also a constructive fixed point. It's a constructive theorem. It tells you how to find that fixed point. Okay? So what we really want to do is construct that chain C. So how do we do that? Well, we start with a triple of bottoms. All right, that's always an element of C. It's the first element. And then we evaluate this function f with that triple of bottoms. Okay, so what should this behavior of f be when all 3 inputs are unknown? You don't know whether they're present or absent. What should the outputs be? Can any of them become known? Yeah, the top one becomes known because it doesn't actually depend on the inputs. Okay. The other two are going to remain unknown. So I evaluate this once, and the top output becomes known, which gives me my second element for C, which is bottom, bottom, and whatever value that reaction produced. Right? But I still have two values unknown, so I haven't found a fixed point yet. So I just keep constructing C by continuing to apply the function f. So now I've got P3 is known, P2 is unknown, P1 is unknown. What changes on the outputs? Well, notice that the top value doesn't change. It remains V1. Okay, that's reassuring because if it didn't, we wouldn't have a monotonic function. If we actually changed value now, we would have a problem, right? But it doesn't change value. It's going to be V1. But P2 is now going to become known, okay? And it'll give us some value V2. And now we have a third element for our set C, where two of the values on the outputs have become known and one of them is still unknown. All right, so now I need to evaluate the function again with these guys. And what's going to change on the output? Well, P5 is going to become known. Okay. The other two are going to remain unchanged. P5 becomes unknown. I now have my fourth element for this set C. Now I know all the inputs. What happens if I evaluate the function one more time? Well, nothing changes. Right? I've reached a fixed point. I have found the value of the function, and this is bogus. This is a set. Sets don't repeat elements. Okay, so those should not be there. Okay, so I now have my set C. It's got 4 elements in it. Which is the biggest in our partial order? Well, the one that doesn't have any bottoms in it is the biggest. That's the behavior of the program. It's the fixed point. It's the least fixed point. Okay, so this is called a least fixed point semantics. And this works for actually a pretty wide variety of concurrent programming languages. All of the synchronous languages have this kind of a semantics where they're formally defined as a least fixed point. And lingua franca has this where the least fixed point occurs at each tag. Okay, and the only thing you have to do in order to be able to use this theorem to prove that the behavior of the program is deterministic is to ensure that each function is monotonic in this flat partial order. Does that make sense? So the one missing element in this, of course, was there a question online?
Yeah. So is this kind of a basic proof structure for these sort of things? So is that something you would normally think of? Okay, maybe I can reformulate it and then use the Clainy theorem.
I didn't quite understand the question. Unfortunately, the audio is a little garbled. Can you say it again?
Sorry. I was just asking, is this some general proof structure that you often use in these things? So just reformulate it and then use the Clainy theorem. Yeah. Did you get it now?
Yes, it's actually an extremely powerful technique, and it can be used for any partially ordered structure, including infinite structures. In this case, the structure is finite, so it's really rather simple. But it can be used for infinite structures. So one situation in which the same semantic framework gets used is in process networks, where the inputs and outputs of functions are actually potentially infinite sequences of values. And now the partial order becomes a different mathematical structure, you use a prefix order. And there's some technicalities in how to apply the Clainy fixed point theorem. You have to show that your partially ordered set is complete in order to apply the theorem, which means that the set includes all its limit points. And that becomes a very interesting technicality in that case. But that technicality, those technicalities disappear in this context because all of these sets are finite and the partial orders have finite height. Actually, the sets are not necessarily finite. So, for example, the set of all possible values in Python is not a finite set. But that doesn't affect the depth of the partial order. Right? It affects the breadth of the partial order, makes the breadth infinite, but not the depth. So it's particularly simple to apply the Clainy fixed point theorem in this context. The other interesting generalization, which is some work that was done in my group, including a couple of very beautiful PhD theses, where you can extend this to continuous time models like differential equations, where the inputs are not discrete sequences, but rather are continuously evolving functions. And in that context, there's some really fascinating corner cases that arise that when you have to look at limiting conditions and the math gets more intricate. But in the context of lingua franca, the math stays really completely straightforward. So there is one piece that's missing here, right? So if I want to, for example, prove that a lingua franca program is deterministic, okay, I have part of the proof as long as, part of the proof is simply showing that every function realized by a lingua franca program is in fact a monotonic function in this flat partial mode. And that's part of the proof. But the other thing that I need to do is show that when you progress between tags, when you replace the function f of n with a new function f of n plus 1 at the next tag, that there's only one possible f of n plus 1. All right, you have to show that that transition to a new function is deterministic. And in lingua franca, that simply depends on the behavior of each reaction being deterministic, because these functions depend only on the state variables of the reactor. Well, assuming they depend only on the state variables of the reactor. Of course, if you implement a reactor that does something like measure the temperature of the microprocessor and produce that on the output, then that will become non-deterministic. Right? So as long as your reaction functions are themselves deterministic, then it's easy to prove that this transition between the function at tag n to the function at tag n plus 1 is also deterministic. And then you get a proof that the whole program is deterministic from that. Okay, so let's take a stretch break, and then I'm going to give you a completely different way of modeling these programs that uses a different branch of mathematics, namely metric spaces.